So our next speaker will be Dr. Thomas Gerds, who's a professor of biostatistics at the University of Copenhagen. Dr. Gerds' research is about theory and applications of statistical methods for binary, longitudinal, and time-to-event data, also with a focus on study design, causal inference, and machine learning for pharmacoepidemiology. And among many other things, he collaborates with the Danish Heart Foundation and associated research groups on registry data studies. His talk today will be a rate is a rate and odds are odds, or no, odds are odd, excuse me. Thank you very much, Dr. Gerds.
So can you hear me and see my slides?
We can, they look great.
Excellent. So my research is not about randomized trials so much, but more about observational studies. And in particular, what's very important is communication. So I want to start out here with the purpose of warming up the crowd for Maya. I will start out with a discussion that someone can have with someone else. So the question is, hey, you look old today. How long does it take you to bike to work? Now, for you Americans, this may seem like an odd question, but imagine a counterfactual world where you have bike lanes. And then the answer could be, okay, it takes me 10% longer than last year. Of course, this person was 1 year younger last year. And of course, we could have instead asked a completely different question. We could have asked about the 5-year risk of cardiovascular disease. And then the answer here, the problem with the answer is that the information is not really good enough. It doesn't really answer the question. And in fact, the information that we get from this 10% longer than last year is comparable to what we get when we look at a 1.1 hazard ratio, let's say for the 5-year, for the hazard rate of cardiovascular disease. Now, the next discussion point could be, I see, so if your bike ride is 800 meters and at last year you rode on average 13 miles per hour, then this just costs a red light, so almost nothing. So the effect would be very small. And the answer, yes, that's true, but my ride is much longer. And in order to be really honest, compared to last year on going uphill, I was actually 20% slower. Maybe I was much lighter last year, whereas downhill, I'm suddenly 30% faster. And when we now look at that, so the duration of the bike ride depends on the baseline rate and the distance. And when we look at the second here, then this clearly would violate the proportional hazard assumption, because on part of the road, the change would be 20% in the one direction, and other parts of the road, 30% in the other direction. And I want to discuss today here 3 principles of statistics, and they are a lot about honesty. So the first 2 are about honesty. We should write down the analysis plan and stick to that plan as they do in randomized clinical trials. When we do analysis of observational study, we should, as much as possible, try to achieve honest inference where we account for all the data dependent steps on the way when we calculate standard errors for our final conclusions. And then we should stick to the correct interpretation and let a rate be a rate and odds be odds. And I admit that these principles are very hard to meet when we are just working out based on what we can learn in a course in biostatistics. And maybe this initiative is, in my perspective, is a key to moving to something more workable. I want to discuss today the story based on an example, and the example is the relation between diabetes and depression. And I'm picking a meta-analysis. I'm picking a cross-sectional study and a longitudinal study, starting with the meta-analysis here. The objective, that's from 2001, the objective was to look at odds and prevalence of clinically relevant depression in adults. And the conclusion, the major conclusion here was the presence of diabetes doubles the odds of comorbid depression. And I can tell you the prevalence was between 20 and 30%. So odds in that case do not translate directly into risks. And further, we need to note here what they have done. They have been discussing several papers, and all these papers had different sources of data, and they were mostly focusing on sources of data where there were both a group of diabetics and a group of non-diabetics. And when we now translate the odds of this study, then to be more honest, these are the odds of ongoing depression on a random day in the life of a diabetic patient. In fact, no matter the duration of diabetes. And these odds were twice as high compared to the odds of ongoing depression on a random day in what I call the meta-analysis mixture population of so far non-diabetic persons. And I would remark that if people got used to this type of information, then they should not have a big problem moving to causal inference with the counterfactual variables and counterfactual hypothetical worlds. Now, the next study form here is the cross-sectional study. And in this study, they have been not able to decide which model they wanted to use. So they have a crude model where the only variable is the diabetes versus non-diabetes. Then they have an age-sex socio model where they adjust for age, gender, and socio variables. And then they have a fourth model, including also comorbidities. And you can see that both the significance changes, but also the odds ratio changes a little bit. And then they also use a model as model diagnostics. They use the Hosmer-Lemcho statistic, and here the p-value was 0.08. And because it was above 0.05, they concluded that this was a satisfactory fit. And I want to get back to that statement a little later. For now, I want to switch to the longitudinal cohort study form. And this here is a paper from 2020, so very, very recent. And here, the first statement in the abstract is a misunderstanding of the meta-analysis that I showed you 2 or 3 slides ago, where the depression is twice as common in individuals with type 2 diabetes. That's not true. It's the odds are twice as high, and that does not translate into this statement that we see here. And then they have a different study form. So they use Cox regression and follow people until the next incident depression situation. And they relate this increased risk of incident depressive symptoms using Cox regression with, here they report in the abstract, the fully adjusted hazard ratio per 1 standard deviation of the marker HbA1c. But when we look at this translation between hazard ratios and risks, then I want to state that the effect, say, on the 1-year risk of incident depression is not very clear from the statement put in terms of a hazard ratio. And it would depend on the baseline rate and the other risk factors, and on the validity of the model, whether we and how we would translate from the hazard ratio into a risk statement. And when we look at the statistical method section of the longitudinal study, then here I have in red corrected what I think needs to be corrected. So hazard ratios do not directly indicate increased risk. They do indicate increased rates. And they do that depending on which other variables are in the model. And as you will see in a little bit, there will be various other models with various other conditioning risk factors, and that will of course change the interpretation. There's one more thing I want to say here, and that's they were censoring participants in case of attrition. And here one has to be aware of that the Cox model also makes an assumption regarding the non-informativeness of the censoring, as we have heard Hendrik discuss quite nicely. Now, when we look at further at the statistical method section, then also in that study, they could not really decide beforehand which model they want to use. So in addition to the crude model, they have the first adjusted model, the second adjusted model, and the fourth adjusted model. And then there were several additional analyses. So in total, for each of the markers that they are studying, they have 15 different models with 15 different condition sets put in one paper. And then finally, they say a two-sided p-value below 0.05 was statistically significant. Now let's look at the results. We see here from the crude model, we have a hazard ratio of 1.44, and then it does change according to what I put into the model. And then people usually like to compare these numbers and draw conclusions from the comparison. However, I'm saying this is a moving target. So the interpretation of these variables does depend on which variables are in the model. So we cannot compare them directly due to the non-collapsibility of the Cox regression model. We look here at the additional models. So here's model 5, 6, and model 13. Then it gives a quite unclear picture. Some of the p-values are not significant, but the conclusion in the paper was then that the additional adjustment was not materially changing the associations. Finally, in this longitudinal cohort study, they were also mentioning that they were testing for whether there was an interaction with gender. And I'm not sure what they would have done had their interaction test rejected. But I guess then the final model would have included the interaction term. And my point here is when we do such model checking, goodness of fit tests, and then react according to them, then the final model p-values do not account for the variability and are inflated low. And that could very well impose important problems here. And we can ask ourselves, are all these models correctly specified? Are these results still significant? And are the conclusions meaningful? And traditional thinking would help us here. They would say, okay, someone should go ahead and check the assumptions of all these models and correct the inference for all data-dependent decisions and also for multiple testing. However, because the proportional hazard assumption cannot be true theoretically for all the 15 models, I don't think it's a very useful way of thinking. Anyway, let's look at this. So goodness of fit tests, they would traditionally use the same data as used for fitting the model, also for doing the goodness of fit statistics, and that would often lead to overfitting or untrustworthy results. It is totally unclear in which order to test the goodness of fit of the model. So when you have 15 variables in your model, then which variable do you start with regarding interactions, linearity, and proportional hazard? So there's some kind of ambiguity, and this could also lead to unstable results. And finally, what would happen if the assumptions are not met? What if the model goodness of fit test rejects? What are the alternatives to the model? And when we look here at the Cox regression model, then Cox model goodness of fit, and this is maybe something you would learn in the course of biostatistics, then the null hypothesis of the model is proportional hazards, linear effects, no interactions, and non-informative censoring. And the alternative hypothesis would be any violation of these assumptions. And there are two possible outcomes. We could either wrongly reject. So we reject that, saying we would say there's a violation of this assumption, and we should then move away from our nice Cox regression model. And this way we may lose some power. However, we could also wrongly accept, meaning we trust our Cox regression model and miss that some of the assumptions are violated, and this could introduce serious bias. And I think we can agree that in this case, bias trumps power, and maybe the roles of the null and the alternative should be exchanged. Of course, this is not extremely simple, and when I have to face this question myself, then this is an analysis that I did in the beginning of the COVID-19 period, where we had not a lot of time to do our analysis. So this was a paper written within, I guess, it was 8 days. So within 8 days, we collected the data, did the statistical analysis, submitted to the journal, and then the editors were doing the refereeing, and this here was the very last statement from the editors of a quite prestigious journal. They were having 2 more queries about our nested case control analysis, and one was they were completely confused about that the nested case control analysis did not result in odds ratios, but in hazard ratios. But I think we clarified that quite clearly. But the other was more severe. We should add how the proportional hazard assumption was tested and whether the test was met. And of course, there was not just one variable. So how, in which order, and there were several other assumptions that are not mentioned here, but of course, as important, like interactions and other assumptions of the Cox model mentioned before. So I was in trouble, and I got 6 hours to solve this. And my solution here was to write the following. We tested the assumption of the Cox regression model, all of them, by comparing the results of an average treatment effect estimate for 30-day risk of severe outcome after COVID-19 infection using a random survival forest. And I was then comparing the Cox model result with the random forest model result, and then kind of concluding from that, but not really. But we got away with this one. Okay, so to conclude here from my observations of the current procedures in applied biostatistics, the epidemiological studies that we are so used to have often a rather vague way of conclusion. So it's actually sometimes forbidden to say the word causal. So we're only getting associations. And if you agree with me, then some of the odds ratios are really difficult to understand, and it's not getting much better with the hazard ratios. And when we do not understand our results, then it doesn't help so much to just rephrasing them and calling the odds ratios for risk ratios and the hazard ratios for risk ratios, because then we're just cheating ourselves. So the conclusions are not very strong. So we should be honest and say they're not very strong. Then I believe that the concept of an independent predictor, which is obtained by comparing crude, adjusted, and fully adjusted logistic and Cox regression models, is a huge misunderstanding. And in fact, the reason is that both the logistic regression and the Cox regression are non-collapsible models, and they target different parameters, and therefore it doesn't make a lot of sense. But the answer is not so far. So hopefully we get to this. We get this implemented. So a great alternative to, say, the 15 unplanned models that we were seeing in the longitudinal study here would be a cross-validated superlearner, which could very well use the loss function of the goodness of fit test, but then use cross-validation or data splitting to make the inference valid. And the superlearner could very well use a random survival forest as one of the learners. And an alternative to an analysis with a moving target, where we all the time, when we change the conditioning set, change the target parameter, then we could instead use a well-defined causal parameter. And that's the part of the beginning of the roadmap. There you have to define what you want to estimate. And this is the first and most important thing to think about. And I really hope that this will become a more general recipe for honest inference. And the challenge is that we need to teach this to many and achieve a lot of good collaborations between biostatistics and medical research. And yes, this was my last slide. So thank you for your attention.
Wonderful. Thank you so much, Thomas. Do we have any questions please feel free to type any questions into the Q&A, or I think you can also raise your little blue hand if that works, and feel free to ask them in person. I know there was one question from the previous talk asking, is the hazard ratio the appropriate estimate to produce in the future? So great question. I love it. In fact, that is one of the themes of day 2 of this webinar. So we'll actually spend a little time in depth looking at first just an overview of the limitations of the hazard ratio, which I think many on this webinar familiar with, and Thomas did a really nice job highlighting again really what some of those limitations can be, even in the context of a randomized controlled trial, as Henrik pointed out. And then we'll talk, so we'll do a bit of that on day 2, but then we'll talk in depth about what applying a causal roadmap and then targeted machine learning looks like in the context of a randomized controlled trial with a time to event outcome, where classically the primary analysis is a Cox model. So stay tuned for that. I would guess the spoiler would be no, in most, if not all cases, the hazard ratio is probably not the estimate we should be targeting, but let's consider some alternatives. And so we'll be coming back to that. Henrik or Thomas, did you want to add anything to answering the question about the hazard ratio? All right, in that case, I will move on to these 2 other questions. So we have from Torkild, looking at data before planned analysis. Years ago, I had a chance to ask Don Rubin about this, and he said he never plans analysis without looking at the data. Maybe it depends on what we're looking for. Oh, this is a great question. Who wants to take this? Actually, Mark, are you online? Do you want to, since we haven't had a chance to hear from you yet, or maybe Tomas, do you want to go first, and then maybe Mark?
I think Mark is having, because Orenda doesn't have electricity.
Can you hear me? This is Mark.
Yes,
oh,
yes,
great.
I can hear you. Yes.
Oh yeah, I somehow got in spite of having no electricity. But you want me to start answering that question about the Don Rubin?
You or Tomas.
Well,
yeah,
no, fine if Mark answers.
Guys, I think this is referring to when Don Rubin says this. He's referring to the typical approach where people first do matching with outcome blind data, right? So you only have coverts and treatments, and you have this kind of observational data, and you need to plan an analysis for going after some causal effect. And then they think of having this kind of outcome blind data. They think of that as part of the design stage, and they feel they're kind of free to play with that because they don't have the outcome, so you cannot really cheat. And then based on that, they decide, okay, maybe I should be trimming out these observations because they cause too much, positivity violation. They call it trimming. And so you're kind of deciding on what the estimate is going to be. And then typically they will do the average limit effect, but in principle, you could even decide that. And so I think that's what he's referring to when he says, I'm always first look at the data before I plan the analysis, and I think that is fine. I mean, in other words, the idea of using outcome blind data to start thinking about what do I really want to define as my estimate of interest, right? Because you might find out that maybe a particular estimate you thought you cared about has no support in the data. So in other words, if you would go after it, you would have 0 power, because you can already see that because there's too extreme confounding going on. So so it makes a lot of sense that if you are in that situation where you have outcome blind data, that you can use that to decide on, in particular, specifying the target estimate, and then there are many ways to do that. But I think this is the background from Don Rubin, where he's relating to.
Thomas, do you want to add to that?
I think this is a good way of answering the question. I totally mean that when you look into this paper with 15 different models, then they have not just used outcome blind data, they have been analyzing the data, and then afterwards they could not do anything more honest than showing everything. And I don't think they are to blame because they are missing a better way of doing this.
That's a great, I think that's a really important point as well, that it's not so much an exercise in gotcha, you did it wrong, but it's that we need new tools that will help all of us do better. And I think that's one reason we're, I think, also excited about this initiative. Yes. So we have one more question before we go to a 5-minute break. So we have a question from Jonathan Bartlett. Is it really true a random survival forest makes no assumptions?
Well, it's a machine learning procedure which doesn't make any assumptions, but of course you can discuss. Then we need to discuss what it means to make no assumptions. So whether it can be consistent in a non-parametric model without any assumptions on the non-parametric model, I don't think so. I think we need to guarantee that some of the things are quite well behaved. In particular, when you have a continuous covariate, then you cannot allow that the whatever true distribution condition on that covariate behaves like a Brownian motion or something. That's not that we cannot identify.
Yeah, so it's more than consistency, right? That's what you're also saying. We need actually theory, which says that this estimator would work and give us a valid confidence intervals.
Yes.
And that's where we have serious concerns.
Yes.
Great. So I think we're at time. There's a question about the effectiveness in subgroup analyses and what are the best ways of doing this. That is a wonderful topic. We will actually touch on that in our third day, talking about the causal roadmap to go after more complex causal questions, including combining both sort of subgroup discovery or treatment effect heterogeneity with rigorous inference. So stay tuned for that. Let's break now. We're going to take a 5-minute break and we'll come back at 2 minutes after the hour. Thank you, everyone.